Hi, I'm Ramon Miranda, your host for Chemistry in Action. In the past two episodes, we looked into measurements. Today, we will begin to discuss how to classify matter. Let's find out what makes mixtures different from other kinds of matter. Mixtures are all around us, in everything we do every day. In eating or drinking, cooking or cleaning, we always see and use mixtures. Let's look for mixtures in this food center. We make halo-halo by mixing bananas, beans, gulaman, sago, leche flan, sugar, milk, and ice. We make fruit drinks basically by mixing fruit bits with sugar, water, and ice. See these two men preparing coffee? They both have the same amount of water and coffee in their cups, but one adds twice as much sugar as the other. This makes the two drinks differ in composition. The drink with more sugar tastes sweeter than the other, but in both cases, the properties of each ingredient, the sugar, coffee, and water, is found in the mixture that is a coffee drink. How much the properties of each ingredient appears in the mixture depends on the relative proportions of each ingredient. The mixtures that we have just shown have ingredients that are themselves mixtures and not substances. Much simpler are those mixtures made up of two or more substances. Gold jewelry, for instance, is basically a mixture of two substances, gold and copper. Mixtures are combinations of two or more substances in varying proportions. The combinations do not involve chemical reactions. All the properties of the mixture are a blend of the properties of each component. You will find many mixtures at home too. Some of these we have already come across in our past episodes. Vinegar, for example, is a mixture of about 95% water and 5% acetic acid. And then, drinking water itself. Drinking water is a mixture of pure water, dissolved minerals and gases, and some impurities. These dissolved substances give drinking water its distinct taste. We can see how water is a mixture when we boil or distill it. Observe the dissolved gases coming out from the boiling water. High temperature causes the gases to escape from the water. In distilling water, we boil it to change it into vapor. Then, we cool the vapor to change this back into liquid. Notice the scum or dissolved minerals in water deposited on the walls of the distillation apparatus after the liquid is turned into vapor. Muriatic acid is a mixture of hydrochloric acid and water. It is sometimes used for cleaning tiles and toilet bowls. Soil is a mixture of sand, silt, clay, humus, and millions of bacteria, fungi, algae, and tiny living organisms. Gasoline, which powers vehicles, is a liquid mixture of different hydrocarbons, including octane, hexane, and decane. Air is a gaseous mixture. Its principal components are nitrogen and oxygen. Other gases in the air are carbon dioxide, water vapor, and small amounts of noble gases like argon, neon, helium, and xenon. We have seen some examples of mixtures we encounter every day. Thousands more exist around us and within us. How can we simplify the study of mixtures? By classifying. We can classify mixtures into three kinds according to their particular characteristics. We will look at the three types of mixtures after we pause for some reminders. Some of the mixtures you saw, like guayabana drink, are those of a solid and a liquid. The solid does not dissolve. If you shake the mixture, you get a suspension. You can easily see the bits of guayabana even after shaking. Later, these suspended solids settle to the bottom of the mixture. A second kind of mixture is a solution. Commercial vinegar is a liquid solution. Look at this vinegar. Do you see any solid particles in this mixture? No, because in a true solution, the solids mixed in the liquid are now dissolved completely. The part of the solution that is dissolved is called the solute. In the case of the vinegar solution, acetic acid is a solute. The dissolving medium is called solvent. In the vinegar solution, water is a solvent. Usually, the mass of the solvent is much greater than that of the solute. Other liquid solutions are muriatic acid, bleaching liquid, and gasoline. Not all solutions are liquid. There are also solid solutions called alloys, which are made up of two or more metals. Some doorknobs are alloys of zinc and copper, also known as brass. The sink is an alloy of aluminum and some magnesium. A stainless steel knife blade is an alloy of iron, nickel, and chromium to which a little carbon has been added. Air is a gaseous solution. This solution we cannot see with the naked eye. Colloids make up the third type of mixture. Two examples of colloids are mayonnaise and milk. In mayonnaise, the oil droplets that are formed during beating spread evenly in the egg yolk. The protein molecules of the egg yolk coat each oil droplet, thus preventing them from coming together or coalescing in a separate layer. The same is true for milk. The protein molecules coat the oil or fat molecules and prevent them from coalescing or settling. If we observe colloids with our naked eye, they will appear uniform or the same all throughout, just like true solutions. But if you look at them through a microscope, You can easily tell their different components from each other. In the case of milk, the oil or fat can be distinguished from the water medium. Colloids can break easily. If we add vinegar to milk, it curdles, showing two distinct phases. Solutions are not so easily broken. If we add salt to a vinegar solution, it does not cause acetic acid to separate from water. Conclusion: solutions are more stable than colloids. How else can we distinguish between solutions and colloid? Ms. Evelyn Josue, a chemistry teacher, will show us how the Tyndall effect can identify a colloid. She has with her two different water samples: tap water in beaker A and turbid water in beaker B. Compare the path of light that passes through both beakers. We can see the path of light through the turbid water, but not through the tap water. The particles of the colloid scatter light and make the path of light visible. After that enlightening experiment, let's pause for a short break. Let's take a look at the other characteristics of mixtures. Earlier, we saw how mixtures are made, involving no chemical reactions. Now the question is, can they be separated back into the substances that make them up? And if so, how? Watch these construction workers working on a mixture of sand and gravel. Using a sieve, they are separating the finer sand particles from gravel and larger sand particles. They then combine this fine sand with cement to make another mixture, concrete. Sieving is a simple and easy way to separate two dry solids, each with a different size of particles. Gold panning is a combination of two separation processes, namely sedimentation and decantation. Large, heavy, insoluble particles settle to the bottom of the container during sedimentation. When the solid is settled, the liquid part is carefully poured off or decanted. This process is called decantation. In the laboratory, we can do a better separation of two immiscible liquids using a separatory funnel. Let's prepare some homemade coconut oil. First, we squeeze finely shredded coconut meat. This method is called extraction. The resulting coconut milk is a colloidal mixture. To separate the oil from water, we apply heat, which will break the colloid. Let's look at how the separation of mixtures is done in the laboratory. Filtration is another way of separating an insoluble solid material from a liquid. The mixture is passed through filter paper. The smaller particles pass through the holes in the paper. The filtrate is a liquid part that, like the smaller particles, passes through the filter paper. The larger solid particles are retained on the filter paper to form the residue. Filtration uses the same principles as sieving. Still another method of separating mixtures is evaporation. We use evaporation when we need to recover the solid dissolved in a solution. One disadvantage, though, in evaporation is that the volatile part, the liquid, is lost. Let us now look at two ways of evaporating liquids. Use this setup when evaporating a non-flammable solution. For example, you can boil off water from a sample of seawater by placing it in an evaporating dish and applying heat. The solid salt is left behind. This is rapid evaporation. Water evaporates slowly from bodies of water. This is the usual source of water vapor in the air. Use this other setup when evaporating a flammable solution like alcohol. See to it that there is no open flame in the room. The setup uses a water bath which prevents direct contact between the source of heat and the flammable solution. We prepare common salt by exposing seawater to the sun. This is called solar evaporation. Solar evaporation of seawater is a commercial way of making salt in some parts of the country. This is practiced in Cavite, Misamis Oriental, and other coastal towns in the Philippines. After filtration through sand, the seawater is placed in shallow, flat beds. The heat of the sun causes evaporation of water. In every 1,000 kilograms of seawater, there are about 35 kilograms of dissolved solutes. Of this 35 kilograms, about 28 kilograms is sodium chloride. As water evaporates from seawater, sodium chloride crystallizes from the dissolved solutes. Sodium chloride is moderately soluble in water. When seawater is nearly dry, the moist salt crystals are raked out of the mixture, leaving the other dissolved solutes in the salt beds. The moist salt crystals are then further air-dried. The salt we get this way contains about 95% sodium chloride. From sugar cane fields like this come the sugar that is in our coffee, juice, or sweetened foods. Sugar cane is a natural mixture. To obtain sugar crystals, sugar cane must undergo several processes of separation and purification. Let's see some of these processes that take place in a sugar refinery. Step 1 is an extraction process. Sugar cane is first cut into pieces, then pressed in big rollers. Extracted from the cane is cane juice, a mixture of sugar, proteins, some acids, pulp bits, and some dirt. Step 2 involves filtration. Filtration removes the solid impurities. Heating causes the filtered cane juice to coagulate or thicken and harden into lumps of sugar. Step 3 involves a second filtration of the mixture neutralized with lime. Step 4, evaporation and crystallization. The heating of the second filtrate removes the liquid and forms a semi-solid product with some crystals. Step 5 is cooling and centrifugation. The semi-dry solid is cooled, then placed in several centrifuges. A centrifuge is a device that rotates at high speed. This separates heavy brown sugar crystals from molasses. Molasses is a mixture of sugars that do not crystallize. To make white sugar crystals, the brown sugar undergoes additional refining. Before we proceed, let's take a look at some sweet reminders. You have seen that many of the things you use every day were once parts of natural mixtures. They were transformed into what they are now by the application of one or more processes to separate and purify components in a mixture. Let us now review some of the separation techniques shown in this lesson. To separate an insoluble solid from a liquid, we use filtration, sedimentation, decantation, and centrifugation. To separate a soluble solid from a liquid, we use evaporation and distillation. To separate two liquids that are immiscible or that cannot be blended, we use a separatory funnel. To separate solid mixtures, we use sieving or dissolution and recrystallization. With this episode on mixtures, I hope you got a fine mix of education and enjoyment. Be with us again as we tackle the subject, substances we use. Until next time, this is your host, Ramon Miranda, saying good day.